our problem. The picture on the left side is the speed control with motor, and the right side is the angle control with the motor. The red line is the ideal input, and the blue line is the ideal input, and the red line is the actual output. As you can see, there is a deviation between input and output, and this will lead to errors in motor control, consequently affecting control accuracy. So based on this problem, we designed many controllers to avoid it. In the beginning, we used the DPDC control to bring the system output closer to the original input. And then we designed the IP controller in the velocity loop. And we also designed a disturbance observer this way. Disturbance observer to cancel the external disturbance. So the first step is we need to know the system transfer function so that we can design our controller. So we employ the system excitation toolbox embedded to define model for motor velocity. And this is our transfer function. To simplify the explain later, we use B over S plus A as a replacement. And next, my team member will explain how we design this controller.
Regarding the controller, to make the system more stable, we use the IP controller in this experiment. The reason is that it is more stable compared to the PI controller. The IP controller structure is as shown in the diagram. The IP get the parameter start with determine the transfer function from this block diagram. Then by organizing it alongside the typical transfer function of the second order system, we can obtain KV1 and KV2 in here. And now the setting the omega n will be obtained from the bandwidth constraint or outline below. In the design, the zero-phase gyrotech converter (DPDC) in a simulate environment, the continuous nature of the system makes it challenging to formulate DPDC directly. Therefore, it is necessary to convert the representation of the continuous system into a discrete system to reduce the design complexity. Based on the aforementioned result, it is necessary to first convert the transfer function into the Z domain for us illustrated in the diagram. Next, for MATLAB, the transfer function can be obtained. The transfer function can simplify into this equation. Now, to minimize path lag, the ZPETC requires the transfer function of the either system to be equal to 1. Therefore, the transfer function to be controlled like this. And as it was not unstable zero, there is not need to additional action. However, in a real-world system, the performance may be compromised due to However, in real-world system, the performance may be compromised due to the influence of disturbance and disturbance noise. Therefore, a disturbance observed of the velocity loop has been designed. Like this arrow. I'll design a filter like this. But a problem was identified. Since this experiment's employee is IP controller, it was observed that the P gain part is unable to filter out this noise, led to a decrease in performance. The noise not decrease. Therefore, an additional filter was introduced that eliminates this noise. However, due to addition of the extra filter, adjustment to PM also need to be made. However, changing PM from the system plus IP controller transfer function to the system I controller transfer function. And finally, we'll check in this group network. So we'll experimental parameter. The input frequency is 1 Hz, and the collision loop bandwidth is 3 Hz, and the velocity loop is 10 Hz. Now the tau is 1/20 pi, and zeta is 1/square root of 2. And this is disturbance. I use loss frequency for the disturbance for this experimental. And I added the 200 to 300 frequent the noise in this experimental for this experiment. And we experimental resource. You can see the blue one is the ideal output, and the red one is IP controller resource. So you can see red is a good control, but the phase lag is large. So we can see the IP controller plus EPTC resource. That is blue one. So we can see the EPTC can reduce the phase lag in this case. And next, this is I add the disturbance and the noise in this parameter. And the green one is not filter output, and the red one and yellow one is add the filter. But the difference between the two filters math is not widened here. So let's zoom in the image. And the green one is p-gain have filter, and the red one is without the filter of p-gain. So in this conclusion, in this study, our group designed the IP controller, ZP-ETC controller, and disturbance observer. According to the experiment, it can be concluded that the IP controller is more stable than the PI controller, and ZP-ETC can stay accurately in the system, and disturbance observer can effectively eliminate external disturbance. It is a thank you.
Okay. Any questions? So what do you mean by this element? Your experiment is numerical simulation, right?
Yes.
You didn't do any real experiment, right?
We try to use in real experience, but our computer will shut down when we command the Arduino in the computer.
So that means you failed to do the real experiment.
Yes.
So you should write a simulation instead of experiment. That is not experimental result, that is simulation result.
Oh, sorry.
Okay. That's why you have a disturbance. In general, you cannot know exactly what disturbance is. It's difficult to have that. Okay. And okay, let's start from this page. You say IP is more stable than PI. What do you mean by more stable? More?
Because he didn't have stable zero. The unstable zero.
Really?
This is in this. Yeah, this the time controller is turned to Z domain, and he didn't have zero unstable zero.
I mean IP and PI.
Yeah, this is the PI had I turn this equation. He has unstable zero, but the IP controller determines zero mechanism. So one will have the.
So you mean?
I mean.
So you mean?
Yeah,
So let me explain. So you mean stability is related to zero. Stability depends on zero. That's what you mean. Can you go to the conclusion?
Okay.
According to your explanation, what you just have said, the first point will be the stability depends on zero. So IP do not have unstable zero, do not have zero. So IP is more stable, is what you mean.
Yes.
But that is incorrect. Stability has nothing to do with zero. Stability depends only on poles.
Okay.
I know。稳定性跟起点有关而已，跟零点没有关系。
Okay.
So the first conclusion is questionable. The second conclusion, DPETC can stabilize the system. What do you mean by this? How can you get this conclusion? Is DPETC feedforward or feedback?
Okay. That's not. Sorry.
Is it feedback or feedforward?
Feedforward.
Feedforward.
Yeah.
Will feedforward
So
affect stability?
yeah.
Yeah. I mean,
Okay.
will feedforward controller affect stability? 前位公司会影响稳定性吗？
不会。
But you say
So
DPC can stabilize the system. How can you get this conclusion?
Sorry, this is our失误。This not can stable the system. He can reduce the past leg.
He can only reduce phase lag and improve the steady state accuracy. 稳态误差，稳态精度。
Yeah.
That's what he can do.
Yeah.
That's it.
Okay.
Nothing to do with stability. And can we go to the very first? The overall graph diagram you show. Okay, here. What is your order of designing the various controllers? Previous, when you present, you begin with DPTC and feedback and disturbance observer. 你们照这个顺序来设计的吗
Yeah.
Really? So,
sorry. Since first is IP and second is DC, but finally is the custom.
so you design ZPTC before you design disturbance observer. 你们先设计。
Yeah.
那你这样
Okay, I know.
then the filter, the disturbance observer will affect your feedback controller.
Okay.
Cross loop transfer function.
Yeah.
So your sequence is the order is a little strange. And then next, what is sample? What is the transfer function? What is the input and output? What is this transfer function?
This transfer function is motor transfer function, and the input is.
Yeah, what is the input and output?
Input is stable input. This is.
No, I mean physical quantity. What is the input? What is the output? from which input to which output。物理量，输入是什么？输出是什么？
输入是 step input， 然后 output 是嘛
No. Step input is what? Which is step input?
is Feedrate.
Is a torque or current or voltage or what is the input?
Input is voltage.
So what is the output?
Output is output is velocity.
Velocity. Angular velocity.
对，变就是encoder 几码后，encoder 几码后的速度。
encoder 几码后，那是位置。
没有，我因为对，因为我们那个还有把位置换算成速度的那个东西，然后去对它
位置可以换成速度。
去做计算，对。
对啊，通信了位置怎么可以换成速度？
就是因为
要经过处理才能变成速度。
对，我们就是有不小心到这部分。
不小心。
因为它是速度系统，所以它是速度系统，所以我们的速度。
这是什么系统？
就是一个。
什么叫速？
就是我们希望它是一个一阶的transfer function， 然后所以我的必须输入就必须输入。没有，这是在这一次。
不懂我的意思。
哦，是。
我只要问你这个transfer function代表什么物理意义，它的速度输出是什么？
对。
比如说从速度命令到速度输出，还是从位置命令到位置输出，还是从 torque 到 torque 到位置，还是 torque 到速度？你们到底输入输出是什么物理量？
就是输入都是速度。
啊？
都是速度，只是我们中间
速度卡面到速度输出。
对，那样子。
OK。What is the unit？ 单位。
单位。
所以你们考虑
一个是 RPM， 就是 RPM 分钟的。
两个都是。
没有 ，RPM 是输出，然后输入我们是用电压。
所以物理量到底是什么？
它就是一个命令，所以
没有，它一定有物理量。So you can see A and B. A and B, they are not equal to each other, right? They are maybe 1.5 or something. Yeah, right? So the input and output, they must be different unit. If you have a velocity input and velocity output, velocity input command, velocity output command. So these two quantities should have the same physical meaning, right? 都是速度。你如果输入是速度命令，输出是速度输出。If you take the same unit, A and B almost be what? 你如果输入是 RPM， 输出也是 RPM，A 和 B 差不多等于1了，它的比差不多等于1了。你们现在是1.5倍左右，啊？
真的吗？
什么真的？你自己是1.5倍左右啊？
不是超出的。它的 response 用不接的话。
你的命令，你要它跑1 RPM， 你希望它变成1.5 RPM。你下的命令是1 RPM， 你希望它变成1.5 RPM， 是这个意思吗？
因为这个是没有任何控制器的，是我单纯输进去而已。
所以我就说这个不是输入命令，所以你们的 input 不是 ，you can go to the previous page. No, the block diagram. Is that block? Is this block? Is the transfer function this block? Huh? Yes. So this is not velocity command. The velocity command should be here. Here is the velocity command. So here should be the torque input and velocity output. So So A and B is not 1 because you have a torque constant. Torque constant. In general, this is either voltage or current. Okay, and you have the angular velocity output, and then integration you get the division output. So when you do the system ID, you have to know what is your input physical quantity. 你要鉴别转移函数，你要知道输入的物理量是什么，输出的物理量是什么。OK， 你才知道它才有意义。OK， and then go next. Okay. Next. Your A to B and B to A.
A to B.
Okay. Next. Okay, here.
Okay.
No. What is your parameter? You didn't show alpha, beta, k, blah, blah, blah. These parameters. Next.
Okay.
So you say your transfer function is this, and then next, you say the ZPTC is just the inverse. So this is not ZPTC actually. This is just what we call the perfect feedforward controller. You don't need DPTC. DPTC is for the case that you have unstable zero.
Okay.
But here, DC, what is the zero in your case?
Okay, so the zero is 1.
Minus 1.
Minus 1.
Minus 1 is stable or not?
I think it is stable.
Huh?
I think it is stable.
Minus 1 is stable.
No.
It's a discrete time domain. Discrete time domain. The stable should be less than 1, the negative. So minus 1 actually should be considered as unstable.单位元。你的连续时间才是左半平面，数位时间是单位元。unit circle. 你的第一 minus 1 should be considered as unstable. Remember in our homework, I asked you 0.95 should be considered as unstable. Minus 1 is larger than 0.95. I mean the negative. 1 is larger than 0.95. 这个是数位时间，不是连续时间。连续时间才是左半平面。
Okay.
Do you understand this? So your design is questionable. And finally, okay, here in your block diagram you have a Z, YZ over UZ, and you have a S in the same block diagram. It's quite strange. Next. You see, in your block diagram, some of them are in S, some of them are in Z. And next. You say you design, you design two types of observers. Okay, here. Some of it, YZ over UZ, and then YS over US. I don't know quite what time you can have. 有些是数位时间，也是连续时间，你把它混在一起。也不晓得怎么弄，I don't know. Okay, and finally, you didn't show the error in your simulation result. You only show the comparison of the command and the output.
Yeah.
You should show the errors.
Okay.
So that You say this one is our DPTC, and next, this one with DPTC. They are almost the same. You say this one is better. We cannot see the effect of DPTC actually. 你在这里说 DPC 也可以改善，我们看不出来有改善。你看这一页跟上一页看起来差不多，你看看起来差不多，怎么看？你要从 error， 你要修 error。Okay, thank you. So next will be group number 5.
Hello everyone. We are group 5 and it's our project title. We try to control the bi-axial system using the NXP 5608 by using cross-plane control. And here's our outline. First, we will design the motion planning for the path and velocity that we will use later to check the constraint control. After that, we will share the simulating and the simulation result after we use the cross-plane. And finally, we will be the conclusion of this final project. Yeah, here's the path that we want to use later. It's kind of shaped in the ice cream cone, and here's the overall velocity. In here, I use the trapezoidal height velocity because I just want our desired part as accurate as possible. And for easier to compute laser and evaluate, I divide my path into 3 parts. The first part will be the upper half circular and start with the point and 0. Finish at the end point is and 0. The acceleration I choose here is around x1.77 millimeters per second squared, and the feedback will get the 0.24 or 24.53 millimeters per second. The second part and the third part is kind of the same because they have the same distance. That's why I designed the acceleration and the feedback and the velocity is same, and also at the same time this acceleration is about 45 millimeters per second squared, and the feedback is around 13.5 millimeters per second.
So now we will talk about the system and the Simulink model. So here just a quick plot of the Bezier diagram for both the x and the y axis, because we just do 2D, so just a code, so it's 2D. This is a basic Simulink model, so I just to use the transfer function we have for both axes and check how does the system respond. We just have a small problem because we should set up the initial condition of the Simulink, so it it can start not at 0, but it starts because here normally we should the common is starting here and not at 0. So that's why there's some weird shattering or something like this. And this is the error, so if you can see it's quite big. So that's why we needed cross-coupling to try to solve this problem. So yeah, first we try to do the identification because we have transfer function, and but during the class we use cross-coupling on a system where we had the controller on one part and the plant on the other part. So at first we try to do the identification, but then there was some I don't know, some uncertainty, and it wasn't working that way, and so that's why at the end we just use a transfer function because we discussed with professor that we would just use the transfer function like this and do the cross-coupling between the cross-coupling without the identification. I think and here also we tried if you remember in the course we talk about the control error using the theta angle, and but this is what is shown on both diagram, because the theta angle, if you try to calculate it, then we use R2 to try and the derivative of the variable to try to calculate it, but then it's not continuous, and at some point it will jump from pi to minus pi and things like this, so it makes the system not continuous, and the result it wasn't working like this. So that's why also we didn't use theta but other formula. Because the advantage of theta would be we don't need to separate all the shape part by part, and we could just use one formula here. That's what we need is okay. First is the circle, the part on the circle. So we use the formula to get the controller with respect to a circle, and then the second and the third part is the straight line. So it's a different formula, and this is it's with respect to time. So at the beginning, till 5 seconds, we use the circle formula to calculate the controller. Then after 10 seconds, from 5 to 10, we use a straight line going down, and then from 10 to 15, we use a straight line going up. So this is the result of the this is combined. This is combined. So in purple, in the center, it's without cross-coupling, and then the outside we almost cannot see it. So it's with the cross-coupling, and here is the controller. So the first without cross-coupling, we have tracking error up to maybe 1 or 2. And here it has been reduced to 0.1. And then logic.
To simplify this, so we try to use the cross coupling because with our system, X and Y are separated, 2 axes. So we try to use the cross coupling to eliminate the effect of acting independently but simultaneously together. So that would reduce the effect of error with a steady state error. Basically, the input and output will be closer together because they're acting simultaneously together. So from the tracking error, after doing all this simulation, we try to look closer into the error. So for the tracking error and trajectory with cross coupling, you see the dashed line with the green line here. It's much closer than not using the cross coupling, which is the red line. It's a little bit different, but some small differences can make a difference. If we maybe change the tuning further or do other simulation tuning with BID or other controllers. Alright, so to look at closer as well, so we check the whole path with the cross coupling. coupling and without the cross coupling. You can see here, without the cross coupling, it's a little bit deviated from the original path. The input is the blue line, and the red line is not using the cross coupling. The green line, which is using cross coupling. The steady state is the error is actually reduced when we use the cross coupling from the input to the output, the error between these two, which give good results in terms of using cross coupling, but it might need some adjustment as well. We encountered some errors by doing the simulation, and also how to track the error and further on, but we figured it out. And from this, we found that the cross-coupling steady-state error from x-axis is around 0.06 centimeter, and y 0.01 centimeters. But when we use the cross-coupling, it gets reduced to almost 10%, 0.009 and 0.0014, which is the difference between this input and output. So our conclusion is that our initial conditions might need some further adjustments, and to make sure that the starting of the position for the path and simulation doesn't start from 0 to 0, but starts from the actual input. And also we need another different approach of the motion planning for velocity profile. We might need to use S-curve or B-spline or any other method that would work with this case. Also, we need to do the experiment. We haven't done the experiment due to some scheduling, some problems we had. So we didn't have the chance to do it. It would be better if we do the experiment itself, then we get the actual error and we can compare. And also we need to improve the tuning of the parameters, especially for the gains and the cross coupling. If we're gonna improve it further to have better results and more reliable and valid results for that case. We might need to implement the zero phase tracking error. I'm not sure how that would affect, because a zero phase tracking error is basically a feed forward. So I'm not sure how that affects, but probably we need to do the experiments and we compare both. If we're gonna use the zero phase error tracking, it might help, but that's for further and future work.
Okay.
Any questions?
Any questions? Okay. Starting from the path, your path.
Yeah.
Okay. The path. Where is the starting point?
The starting point is, I said,
The right corner.
Yeah, 10-0.
Why did you choose?
Because it is easier for me to design the time. Yeah, because we have the time function for each path, and at the time of t equals 0, it's easier for me to design the time when it is 0.
Because when we do for example, the cutting or the contouring, for this kind of case, you have a sharp corner.
Yeah.
These two are not so sharp, right?
Yeah.
So the better choice of starting point and ending point should be here. So that you can avoid passing through the sharp corner. You can do these two are not so sharp. So I end it here. And then, so like you have a cutting point this way and then move. You don't need to pass it through here.
So you wouldn't need a smoothing corner by that side.
For this. And this one is quite, not, is much better than this one. That is That's one point you need to consider.
Can it be one of the reasons why the system with the identification didn't work? Because like the main when our simulation with the identification, the main problem was here. It was jumping from here to here.
Yeah.
Is it because of this sharpness?
But next, you go to the next. For your for your motion planning, you reduce to 0 speed at the corners. So that problem should be, reduced to that.
But because the input of our simulation is not kind of time related. It's just the path.
No, this in the velocity I write here, it actually have like 12 digits later. But here I only use 4 digits, so the velocity here is not really 0. It's nearly equally 0. It's not really 0.
Okay. Yeah. So I mean, the starting point is normally we need to consider that. Yeah. Okay. For here. And also your title of you go to the first page. First page.
First page.
Yeah. Your title is country control.
Yeah.
But next in your simulation, we didn't see any control error.
Yes, tracking.
You show only tracking error.
Yeah.
Oh wait, that one.
Which one?
But
So
the function is for
the one-
country control, right?
That's tracking.
Yeah, that one.
Next, there's a figure, lower left. You have 2 figures.
Yeah, that one. Here.
This is
Yeah,
control error.
this-
That's why I want to ask what are the 2 figures in this
Oh, okay,
one?
yeah, so
We
that
cannot see because it's too small,
It's too small.
especially on the old man.
No,
I cannot see even here.
Alright, so it's too small. It's not here.
I'm not sure you can see.
That one is theta, and that one is a controller also.
So this is control error.
Yeah.
So you should enlarge this one.
Controller using theta.
What is theta?
Theta is the
Oh, theta.
yeah, theta.
Oh, so this is not real control error. This is approximation, right? Not real control error. You should show real control error. Because you have the output next. You have the actual output, right? You have the data. You can compute the real control error.
Yeah, okay.
Because you have the desired case and you have the output case. You can compute that. And finally, your conclusion is I have that page. Previous. Yes, this one. Your conclusion say that cross-harmonic control can improve the tracking error. You mention nothing about control error. Normally, CCC does not guarantee that you can reduce tracking error. CCC guarantee you that you can reduce control error, not necessarily tracking error. Tracking error should be improved by feedforward control.
But the thing is that without no control error in here, so I thought that we just need to add extra.
Actually,
information.
yeah. I mean, in that summary, page, I mean, summarize the other previous. The previous. Yeah, this one.
The way
It should show control error.
Yeah, I really have a control error. When I calculated control error because I didn't use the simile. I used my own code for that, and the control error showed me that it's all over this.
No, control error
Within the time,
needs to be computed, overnight, and it's not so simple.
Yeah.
Not like the tracking error. Tracking error you
Yeah, just
compute quite
the
easy.
difference. Yeah.
Contour error, you need to do, for each point, you need to find a minimum distance. For each point, you need to find. So if you, for the whole contour, suppose you have 100 points,
Yes.
you need to perform 100 attenuation.
Exactly. That's why when I tried to do it, the error was too high and almost the same with or without. But because
How
I
come
did
you
something,
have it too high? It
yeah,
should be not so too high. You
Yeah.
just compare
I
the
just
distance.
exactly. But when I did it, I did something wrong with the calculation, and I didn't get any good results. So I just forget about it. That's why.
Okay, finally, what is the number you show here? For example, 0.0671. What are this number?
This is a distance, right?
No, I mean the whole case. How many data?
I do the average.
What kind of average?
The overall average for all of the path.
I mean just average.
Just the average.
You didn't take any absolute value. You didn't take any.
Yeah, for maximum because it's a distance.
The maximum value would have been maybe better. Like, you know, the maximum error, so we can see that.
Is it maximum or?
No. We should maybe have a.
So this is
the average. But
This is the average, absolute average,
absolute average. Yeah.
not looking square, not
No.
square, not the maximum. Not
Yeah. As the absolute.
So you have to mention this as well.
Yeah, I didn't put it in the equation, but I should have.
Because you put the error and RT minus YT, no absolute absolute sign, no summation
And no average thing. Yeah.
There's nothing showing here.
Okay. Some of the information here we can.
And there's one more point. There's you mentioned about the transfer function. You go to the previous. Here.
Yeah.
You say the phase margin is 0.74 degree only. This one. Degree.
It's
This means that it's almost unstable. The phase margin is very small. Maybe you misunderstand something. This one is closed loop. Normally for phase margin, we are talking about open loop. Open loop transfer function, so you find the crossover frequency. And then the phase, the corresponding phase and gain. You understand what I mean? This is open loop. Unity negative feedback, which is a open loop including the controller. So the closed loop is G over 1 plus G.
But here it's closed loop, right?
No. Here is closed loop.
Yeah.
This is not closed loop. This is open loop, including the transfer function of the controller and the plane. Okay. This is what we call feedforward transfer function. Feedthrough transfer function. So it's G over 1 plus G. That's why we say when G equals -1, this is dangerous. So we found the gain of this when this is 1 and the phase is 180. That means it's -1. So we have to far away from the gain is 1 and the phase is 180 degree. So when you plot the body plot of this, you have a body plot of this, then you will see the so-called 0D. This is what we call crossover frequency. When you find the corresponding, this is magnetic, and you have a phase. You have a phase, and you find the phase angle here. The distance from this phase angle to 180, -180, plus or -180. Then this is phase angle. Yeah. If you are here, then this G will be -1, so it will be unstable. This is what we call phase margin and gap margin. But this one, this G is already this one. Is this.
Yeah.
So you cannot. So maybe you have a misunderstanding.
It's not useful.
Yeah. Okay.
Thank you.
Any more questions? Any more questions?
Maybe just a question, but on the other group, like the group before us and us also, how would you do if you have like if you want to do the ZEPTC, but in continuous time? And
In continuous time, there is a continuous version of DPTC.
Okay.
But because when we will implement, we already implemented in the discrete time. So I also prefer to use the discrete time DPTC. So when you want to design the DPTC, you can first design your feedback, feedforward, or everything. And then you find the discrete time transfer function, crossroad, and then design the.
So then if we wanted to do the EPTC, then we
yeah.
would have to transfer this in discrete time.
Yeah, just this one. Transfer this to discrete time. Then you design the GPTs for each.
Because continuous time is not good for.
Continuous time, yeah, it's not, because you also need to consider your discretization when you implement it. Yeah. Any more questions? Okay. No more questions. Thank you. So finally, group number 6. Group number 6. I think your common problem so far I see is that you begin to do this project too late. So that when you encounter a problem, you do not have time to fix it. Right? Right? Just like your motor, you need to do experiment, you say, well, this has some problem. Actually, if you do it a month ago, then you have time, to figure out it's a problem to fix it. You too, you want to do experiment, but there are some problems, so you cannot, fix it. It's unfortunate.
Hi everyone, today I want to introduce my topic, the bi-axial counter-arrow estimation and the NURBS. Here's my content. It brings the background of making my average and then calculate. First, my background in computer design and manufacturing. Math NURBS is commonly used in curve representation method. And although the efficiency is high, there may still be error between the design model and actual times. And in order to control the machine error, it is necessary to evaluate the fit accuracy between the design model and actual model. And existing research means performs the visualization by drawing the diagram, error diagram. And however, this method requires a large amount of not suitable for the real-time evaluation. From this study, I hope to propose a direct error evaluation method to improve the efficiency of NURBS term generation and optimization. Next, my motivation. In this study, we draws an error distribution diagram to analyze the fit between the NURBS curve and the point P data, which require a lot of visualization work. And to solve it further, this study proposed an error parameter E to quantify the fit error. This is my method. And from the counter error definition, I define a parameter E, and that is similar to the counter error. And the tangent on the curve C, and the vertical is vertical from curve C to point P data. I call this vector is like a counter error, it's the error vector. And how to calculate the error vector is P minus C, and then multiplied by the differential C equals 0. And equals to the following equation. And we need the unit vector of the curve C. And in the end, we can get the error vector equals to n plus this plus this. And our design for the NURBS, I consider some point is in this diagram. Consider some point as the desired point. And we decide a NURBS that free is free and a control point and not. In the end, we can get the counter error. Now result in a diagram. So we show the arrows in this plot. We can calculate the error parameter to get the information about the fitting error between the NURBS and the point. And the parameter of the NURBS can reduce the fitting error by how to know the scale of category of the parameter should be sure without a plot diagram. And we say that parameter E is a tool to get information about the fitting error without a plot diagram. And then the fitting error is absolute value of E. And the symbol of the E represents the position of point referring to the design point. And if the parameter E is smaller than 0, it means that the points are closer to the point than the NURBS. And in the other set, if the arrow is bigger than 0, it means the point is more close to the NURBS than the point, the actual point. This is what I
Any questions? We'll go to the so you next. So you present the result from some paper, right? No. So
reference. Example.
What is the difference between yours and theirs? 那个差别是什么？可是我们文献维度了啊，你不是
参考书里面的一些题，
参考，你们的跟他有什么不一样没有？什么东西不一样？
它会不会有定义性？看会不会有那个东西？会不会有？
如果你们报告他也没关系啊，你就讲清楚就好了。哎，我只是要了解，你们是报告他的，还是你们有另外的一个跟他不一样的方法？哎，到底是哪一个？我只是要了解这个而已。
跟它不一样。
啊？
跟它不一样。
对，是什么样的不一样？我想要了解一下，哪边地方跟他不一样？啊？好，没关系，待会再讲这个。你们到那个 can go to the NURBS definition of the NURBS. You define the NURBS. Okay, NURBS. Here, your degree is 3, and how many control points do you have? Okay, so P1 to P10 is not control point.
No.
So you have only 4 control points. Next, another previous. So you have only 4 control points. Huh? 4. That's why you have the notch defined this way. Now go to the previous one. The very, yeah, this one. What is the red line and blue line represent?
There's many terms.
Huh?
I said this C curve.
What is C curve?
It's a NURBS. P data is
No.
it's C curve and in point.
What is a P? I don't understand it. What is a P? Can you? I don't understand how. I don't understand. So, C is the NURBS we want to follow.
Yes.
Is a desired case.
In Tracker is you
Huh?
want to adjust the width or some parameter to fit this curve.
So you mean the blue line is the one we want.
Yeah.
And you want to design a NURBS to fit the blue line. It's a little strange. So that means maybe you are given a set of data points. So next. So here, no. So P1 and P10 are a set of data points you are given. and you want to find a NURBS curve to fit this data point. That is your problem, right? Okay. You have to explain this clearly at the beginning.
Okay.
Otherwise, nobody understands what you are talking about. It's a little confusing. Okay? Then, in this case, there are many choices. Why do you choose that? You need to choose degree. You need to choose the control point. You need to choose the max. How do you choose the three in order to fit into I cannot see your idea. And then I also do not understand the E. Can you go? Yeah, I don't understand this. Can you go to the video? The blue line and black line, this one. Yeah. You said the error vector is E, right?
Yeah.
How do you define E? You have a set of points here. And this is your NURBS curve. So what is E? What does this mean? This one, your point may be here, not here. There is no point here. 你可能这里没有点啊。
我们一点一点去算。
从哪边一点？从上面的一点还是从下面的一点？什么叫一点一点？是从下面一点一点，还是从上面一点一点？
是从上面。
所以你从上面一点找离它的最短距离，不是从下面找它的最短距离。可是你从下面你的分析好像是从下面。You find a tangent vector and then inner product and so on， 有点对峙，因为你上面不是每个点哦，你上面只有一些离散点 ，you have only some, distributing points. But you define the so-called E from here to here, but you do not have a curve here. You have only data point here. If you have a curve here, you don't need to do the fitting already. 你如果有一条线的话，你就不用什么 fitting 啊。You understand? So next, I still do not understand what you are doing here. You have a P is the point you have. What do you mean by this? dc dp, what is dc dp? And what is the meaning of this? I cannot understand this. P is, so you mean this is P minus C, and this is the C dP usually from the paper.
课本，然后第一句算。
这怎么来的？这是什么意思？什么叫做 C 对 P 的微分？什么叫做 C 对 P 的微分 ？P 是一个点而已，什么叫做对它的微分 ？This means C is function of P. C 是 P 的函数吗？什么是 P？
应该是 dc dt。
啊
dc dt。
啊
dc dt。
dc dt， 那 dc dp 是 dc dt。dc dt. So evaluated at a point, and And this TC, go to the previous one. TC is the point you choose, like a coupling point. Right? You choose this point, you find the dc dt is this, like this vector. And p minus c is this one. Okay? And then you found the next. You want previous one. You want to find which c, which tc that will make this 0. Okay, so that means also the previous one. You want to find the t, this point that will. I understand. You have a data point somewhere. You have a data point somewhere. You want to find the TC that will also follow to this tangent. You want to find this. Okay? And then what is your E? Is E is this distance. So that means you want to find for a set of data points. You want to find the minimum distance from the data point to your NURBS. Okay? So this is the indirect contour error. Normally contour error is from the actual point, the minimum distance to the desired case. Actually, this is your desired case. The NURBS is not your design case. So you want to find the minimum distance from here to here. But now, you do the reverse way. You find the minimum distance from here to here. Okay. Okay, next. So this is the point next. Oh no. Okay. So what the uninormal vector of curve C. This uninormal vector. I don't understand. So this normal vector evaluated at where? Which t? This normal vector evaluated at TC of what? This is not go to the this is function of time, right? So which t you evaluate? TC. If this is TC, then next. The video. Okay. Then it's this one. Right? The N is already this one. Unit vector. And you product with this. So actually there is not it's already actually they are parallel, I should say. So you don't need to do this way. It's already this one is your E. Huh?没有，都是纯量。你只是把它变成那个大小，你把它其实你取大小就好了啦，就不用用这个这么复杂去定义它。你其实这个 your vector normal vector actually is parallel with this one by the definition of TC。因为你 TC 是那样定义的，所以这个就跟它平行。所以你只要取大小，就会变成一个纯量。取那个平方降价太深厚了。OK， next。 this one you have this, and then next. So you have so here you choose the only 4 control points. Want to fit into this. So these points are given by you like you want to try. So you provide a set of points, and then try to find the NURBS to fit into this. Okay. So how do you choose this? What is the process you choose? That is a key point. 你到上一页。Okay. How do you choose this? How do you choose this? How do you choose this? 你们这些是怎么来的？
这些用的上一点多，然后去
Try it later. Just try it later. Do you have any algorithm? No. Just try it later. You should have some algorithm. So because there are many choices for this. According to this, you are given here. Okay. Okay. And then, so you find, for each point you find the so-called PC. You find the so-called error. This error is similar to contour errors, right? Okay. Okay. Now I understand better. Okay. Any questions? And finally, let me ask some. Can you go to the previous? The very first, maybe the second page or, yeah, here. You say you have some terminology. Error cloud diagram. What does this mean? Error cloud diagram. Huh?
It just means the error when it shows in the diagram.
Oh, that is. And next, you have a error distribution diagram. 所以是一样的意思，是误差，然后把它画起来，就是 error plot， 不是 diagram，diagram 应该是那个方块图那种。哦，好，那你的图那个是 plot 或者 B 的。OK。Any questions? Any questions? Okay, it's almost time. Okay. And here, do you have any more things to do for them?
No.
No. Okay, then that will conclude this semester. Okay. Okay. Any question? Okay. I will finish your grade by this weekend. I will submit the grade by this weekend. Okay. Any questions?
No more classes.
No more classes. Happy New Year's. Okay. Okay. Thank you.
I'm taking this course at a time. What I need here are we have to do separate for each course. Yeah, this is the application.
and this is the
for my last exam, I would do it
also
earlier.
two courses I have different. One is
What?
so you
因为它这个是为了讲这个系统，理论上是这两条线。
不是，你有没有说那个你一定要把我的，比如说你要知道它的速度。